Good morning, everyone, or afternoon, or evening. How's it going? Today, we are going to be taking a look at pathfinding algorithms. Pathfinding algorithms are a common way of basically figuring out a good path from something you get from one point to another. So before we get into that fully, what I kind of want to do is I kind of want to consolidate our map code that we wrote yesterday, or not yesterday, last week, so that we can make it a little bit more useful and actually reuse it here. Because if you're going to pathfind through something, we want to be able to visually see that pathfinding happen. So let's see, let's create our index.html, put that in there, pathfinding. Then I'm going to, well, let me create my script first. Create my script. I'm not going to put anything in it right now. And then we're going to put that in here. JS. And then we'll make ourselves a canvas because that's what our map requires. Canvas width equals, say, 500 pixels. Height equals 500 pixels. Remember the reason we do the width and height this way we covered last time. Now, let's see. Let's open up a new window and let's go back to our previous example. Actually, you know what? What I want to do is I just want to go up one and grab all of the video examples, because then I can just swap between them more easily. And we don't need the terminal for now. So let's see, making a map. This is what we did last time. Let's see what we got here. Where is our actual map code? Bunch of different stuff here. We got a mouse move that handles some dragging the map around. So let's see, we come in here, there's the mouse wheel for scrolling. Here's the actual getting the context. We got a couple draw helpers. And then we've got a bunch of stuff in our actual map. So what I'm going to do is I think I'm going to copy this entire file, come over here, and I'm going to make a new map.js. And what I want to do is I actually want to kind of maybe make a class for the map that just knows how to render itself to a canvas. So we're going to say class map, paste that in there. Bunch of stuff is going to go wrong with that because all of these things. So what I want then is I want to write a constructor. Now remember, constructors are how we create the new object. So this is similar to using a factory function or just using something equals new object. It's just a little bit more standardized. So the first thing that we're going to do in here is, we're going to put an ID, canvas ID, okay? This dot canvas object. We use canvas object in a bunch of different places. Remember, this says it belongs to the instance of the map that we're currently working with. And then I'm just going to get element by ID, canvas ID. And the rest of these, let's see, the image holder, map width holder, map height holder, cell size holder. I don't remember. Oh, I think these were actually text fields. So I think I can get rid of those. I can get rid of the generate map button. The hidden canvas, the save map button we don't need. The hidden canvas I think we might actually need. So that could be important because we do need the hidden canvas to remember render our map layer onto that canvas. And then as soon as there's we use that as the image that we actually drag around. I don't remember what image holder was. Let's pull these out for now. And let's just put them at the top in case we need them later. All right, so previous X, previous Y. This is for the event listeners. What we can do is we can actually take both these event listeners and pull them into the constructor because these only need to be run once. They need to be run once when we first register with the canvas. And so we have render map. That's probably going to end up being then this dot render map. Oops. Because that's going to be an element of the map. The diff, max zoom, map zoom level, etc. So let's say this dot map zoom level. Well, we'll get to that actually because that's lower down. So yeah, maybe I just will say this dot map offset x, this dot map offset y. And then down here, this dot map zoom level, like that. So now all of these become elements that are available to the, what am I saying, to the class, to the instance. Okay, context. Sure, let's pull that out, and we can say instead of const context, we're going to say this dot context, and it's going to be this dot canvas object, which actually I should do up here as well. This dot canvas object, this dot canvas object. We're just kind of slowly pulling all these functions into here. The shape, that can actually be a function on the class, and you notice if it's a function on the class, we do not need the function keyword. And so in this case, I don't need the context. I just need this dot context. Actually, shape and line are really more helper methods, aren't they? And I think we need these in different ways. So I'm actually going to take these, oops, and I'm going to put them at the top of the class. So these are not actually part of the class, these methods, because I might want to use them in other places. And these are just things that I want to be able to access and call. The main reason I'm doing this is because we may actually not be using the main canvas context to do this. And so I want to be able to verify that. Okay, so this is a comment. We can get rid of that. Map offset X, Y, zoom level, the min zoom, max zoom, start map X, start map Y. Min zoom and max zoom, I'm actually going to take these out of here and put them to the top here, because these are just constants on maps in general. I'm not going to want them per map. Down here, map offset X, map offset Y, those should probably be, well, we've got them in here on the this. Offset X starts at 0. Offset equals 0. So then we get rid of these. The map zoom level, same thing. Map zoom level, oops, equals 100. Okay, then our start map X and start map Y, those are constants. Those don't really ever change. So I'm actually going to pull those out to the top here as well. I could see occasionally wanting the map to maybe start somewhere else for a specific map, but in that case, you just pull them into the constructor, which wouldn't be too hard to do. Start map width, start map height, and cell size. I'm actually going to pull these all out as well. These were lets because we're actually changing these based on text fields that people are entering. But actually, I think the width and height, I kind of want to pull those in the constructor. So I'm going to leave the cell size here, and then I'm going to pull these into the constructor. Width and height, and we'll put it on this, and we'll say width and height. And because that starts off at 1,000, I'm actually going to set these as default parameters. So if I just give it a canvas ID, it'll create one of 1,000 by 1,000, which should be totally okay. So let's take a look at what we need to do next. Keep going down the list here. The tree. Whoops. Yeah, so the tree is definitely something that belongs to the map as well. Though I could see an interesting case where the map doesn't own the tree and the tree just gets passed into the map. That could be interesting. So start map width, that's going to be this, because it is part of, oops, and then this dot. We do need to pull the tree into this code as well, but that code was already kind of set up to be able to do that. And in fact, we might just be able to import it from here. Draw map. Okay, that's an important function. This is, I believe, actually, oh no, this is the complicated one. Okay, so let's indent that, because now that's going to be a function, or a instance function. Okay, context. So hidden canvas. This is where hidden canvas comes in. What I would like to do here in the previous one, I have my canvas and I have my hidden canvas here. We can actually create that canvas. This is kind of a hint. You can actually do a lot of DOM manipulation, especially rendering to a canvas, without actually putting it in the body. So what I can do here is if I come up here, I can say this dot hidden canvas equals document dot create not create attribute, element, canvas. I'm not going to add this to my body. And what that means is this canvas is just going to be kind of floating in memory. It never displays on the screen. It never even gets rendered into the DOM tree, but I can still grab its context and render things to it, even so, which is totally fine to do. And so that's kind of a thing to bear in mind with this. There's a couple occasions where you may need that. You want the ability to actually hold on to an element, like maybe if you're trying to figure out how wide text is going to be, the really only good way of doing that is actually to add that text to an element and then see how wide that element is. For that particular case, you do actually need to attach it to the body just so that it renders, but you don't need to keep it attached to the body all the time. So you can attach it, do your check, and remove it. Kind of expensive, but it can be useful sometimes. But same with this canvas. If I say this.hiddenCanvas.getContext and I set the canvas width and canvas height to this width and this height, the start map width and the start map height, it'll render fine. It doesn't actually need to be on the DOM to do this. If that turns out to be not true, then I will add it to the DOM, but I'm pretty sure. So start map X, start map Y, those are constants. Start cell size, this is a constant. These are instance fields. Okay, so we've got our shape. And notice this is important. The shape is not an instance method. And so I can actually pass in this hidden canvas context. Totally fine. Draw count. This was just for that. So this is going to be this.tree. Recursion over the cells. This is not actually anything that has really to do with the instance because we've already got the tree and the context. So we know how to do that shape. We know how to do all this stuff. Render draw. We know how to do that shape. Lines. Another recursion of the tree. Forget why this was. Oh, this is to draw the actual or red boxes around it. We might take that out at this point. Okay, render map. This is a very simple one. So this is going to be this.context, and now this.context draw image, this.hidden canvas. I'm actually going to put these on new lines because that's just, I like it better that way. Now you can see a lot of the different instance stuff comes into play because all of these are on the instance now. This. And the main reason I'm doing all this work to pull this into a class is because then I don't have to worry about any of this code anymore. I can just be in my main script and just say, hey, here's a map. It needs to render. And it should just work. Draw map, render map. We don't need that actually. And all of these have to do with changing the various fields and generating the actual map as well. So I'm just going to get rid of that, get rid of the save button, and there we go. So now we've got our class, about 200 lines long. Oh, hidden canvas, we dealt with that, and I think the image holder I don't need. Yeah, I never actually use it. So here's our map. This uses the tree. This is basically what we covered last week. And so what I'm going to do is inside my index.html, I'm going to put it up here. Script. Source equals map.js. Script. Now you might be wondering, well, why would you put it up here in the head as opposed to down here in the body? I put this script.js in the body, and this is the reason we do this is because in case it needs to manipulate any DOM elements or do something with DOM elements, the browser reads top to bottom. So this canvas needs to exist before the script, so the script exists at line 12. Everything in this map, this has nothing, does not actually pull anything from our DOM. This is a helper method that we've used that gives some good functionality, but it doesn't actually do anything until we initialize it. And we're only going to initialize it inside this script. So I definitely need this script to be loaded, before this one, and putting it in the head just means it'll be there. And this also clearly indicates to people that this script is not actually doing any DOM manipulation until it's prompted to. Because this is not the main piece of work that's going to be doing your business logic. This is just a helper because it's in the head. So it's just a convention. Now in my script, I'm going to actually declare my map as new map, and then I'll give it my ID of the canvas. Okay? And then I'm going to say map dot, you know what? If I go into the map, I think I have to draw it before I render it, right? Because render won't actually do a draw. We might want to fix that at some point. So draw map, map.render map. And notice I'm not attaching anything to the canvas. I'm not handling zoom. I'm not handling any of that double buffering, anything on the tree, anything like that. I'm just saying render the map. So now if I take, oops, if I take a look at this, what browser is this going to open in? Wrong one. All right. Grab this, pop it in here. It does look like there's an error because it's not working. Let's see what that is. Tree is not defined. Well, that makes perfect sense, right? We didn't actually pull in our tree yet. And tree is necessary for the map because the map is using our quad tree to actually store its data and do rendering. So I'm just going to go in here and I'm going to, I think I can control copy this and it makes a copy. There we go. Tree, I'm going to come up here as well and put that in here. Oops. Source equals tree. Yes, this one. Thank you. Good. My autocomplete, for some reason, is not working the way it should. All right, let's try that again. Empty is not defined. Empty is not defined. Shouldn't empty come from tree? Oh, you know what? That comes from the wave function collapse. So here's our wave function collapse rules. I don't know if I want to just copy that. I don't actually need this right now. I don't need this at all. So what I'm going to do is I'm actually going to define these in here. As 0 const wall. Because I'm not doing a like landscape map at this point. I'm just want to show something that has a couple of obstacles for people to run into. Const yeah. So let's just do that for now. We got empty and wall, and we're not doing a wave function collapse, so I don't need to worry about it. Colors is not defined. That's fair. Colors, let's see. Empty is going to be white, and wall is going to be black. These are just things the map needs to know. Probably at some point we'd actually want to pass those into the map, and then even make like the wave function collapse take the map as a parameter and just say, hey, here's our map object. Go ahead and perform a wave function collapse to populate it. Whereas the map itself, these states and these colors should actually be something that like the map doesn't necessarily need to know about. That is also not what I want. All right, what's next? Oh, there we go. Okay, it's not completely working super well, I think. And I think that might be because, yeah, for some reason the map itself, oh, the rectangles are too small. So this is only a 400 by 400 rectangle. So you can remember when we drew our map, we have to redraw a rectangle every time because otherwise we get stuff like this. I'm pretty sure in the map, it's not actually taking our width and height into account when it's doing that render. So let's take a look at that. If we come down to render map, yeah, so you can see these are hard coded. So this should be this dot, actually we should be using start map X and start map Y for this. Just because I know they're 0, but it's just cleaner. Start map X plus this dot start map width, start map Y, and then this is going to be start map X plus this dot start map. Basically, we're just drawing a rectangle, and it was drawing too small. So we need to put it in here so that it draws right. This dot start map height. That is not height. And then here, this is going to be start map X, and this is going to be this start map Y plus this dot start map height. Now, if I come back here, load, that should work okay. This is actually a really big map. I don't want as big of a map to start off with this. So I'm just going to go in my script and I'm say, hey, instead of a map that big, give me one that's 200 by 200. Easy. Now you can see the power of this class now, because now I just get this. Ooh. You know what's really interesting about this? The map is actually drawing its own background. And so that's why it's super small. It shouldn't the map actually should not be drawing its own background. The map shouldn't care about this. This should be something that belongs to the canvas. So what I'm going to do is I'm actually going to take this shape that I know I just put a bunch of work into, and I'm going to pull it out. And I'm actually going to make a new thing here, and I'm going to call it render. And then here, I'm going to have my 0, 0. I'm literally going to undo what I just did, basically. And I can actually say canvas dot, I need to actually get the canvas for that. Const canvas equals document dot get element ID canvas. And I could say canvas dot width 0. Canvas dot width. Canvas dot height. This is going to do basically the same thing, but then it's not going to care how big the map is. The map will not have to be the size of the canvas or larger, which you could see that was a bit of a problem. Canvas dot height, and I'm actually going to take my render map, put that in here, and now just call render. So now the map is no longer responsible for drawing the background rectangle to reset the canvas, which is probably a good thing. Okay, well that broke. What happened? Cannot read properties undefined. Oh, because it doesn't have a context. Canvas. Canvas.get context. QD. And now we have our context. There we go. There we go. And now, oh, it's still not doing this. Oh, because the canvas, the map doesn't know how to re-render. So when I pan the map like this, it doesn't know it needs to tell the canvas to re-render. It just knows to re-render itself. So that's kind of fun. What I should do then is I should actually make the map take in a new render. So like a render method here. Let's do that. Render function. And then I can say this dot render function equals render function. Okay. And now instead of calling this dot render map, I call this dot render function. And that will actually tell the canvas. So this is an example of event passing, right? So the map said, hey, something happened and I need to re-render. So instead of re-rendering itself, which ends up doing this, it's actually going to go to the canvas and it's going to say, wow, something really broke there. Oh, because I didn't actually pass it in. It's going to go to the higher up system and it's going to say, hey, I re-rendered. Here's a callback. Please do the re-render that you need to do, which ends up calling map render map, but it also does its own stuff here. Let's see if that works. And now that works. Now you can see we can drag that around appropriately. And I could even put a second map in here if I wanted, and they both would pan. Might not be the most useful thing ever, but maybe we'll do that someday. All right, tiny little map. Cool. We got our quad tree set up as well. Now I need to be able to add and remove stuff from the map. Problem is, well, so what I could do is I could actually say like map.tree.add. That's actually probably fine for now. I could add a function on the map as well that knows how to add and remove stuff from the map. The reason that could be kind of useful is if we want to actually not use a quad tree in some cases and let the map determine what rendering system it wants to use. That could be kind of nice. I'm not going to do that super right now. So let me just look at my quad tree real quick. What are the methods on this? Okay, so it's set xy value and get xy. Okay, so what I want to do is I want to add some obstacles, right? So let's say map.tree.set 10, 10, 1. 1 being a wall. Let's just verify that works, and we'll add a couple more. Nope. Cannot read properties of undefined reading x at tree.set. What? Tree.set. What was the problem here? Tree.set. Undefined 133. 133. Current.x. So we don't have a root? Is that what you're telling me? That's interesting. Current. We have a current. It has... Oh, it doesn't have an X. Oh, it does. It has an X and a Y. Weird. Well, let's pop that in here. Log current. Okay, we got some tree nodes. It's going down. It's coming down. It's checking. This one has a height and a width of 0. Okay. And an X and a Y of... So somehow this fucked up again. We're not getting our... What are we looking for then? X current dot Y. Y, X, and Y. We had this problem before. Okay. We're looking for 10. Somehow we end up at 7. You know what? I think 10 is actually off the map. I think that's the problem. Because if we take 250 and we divide it by 20, or 200, and we divide it by 25, yeah, it goes to 8. So that's why we actually asked it. Okay, well, this is an interesting case that we should probably set up with our tree at some point, is like when we actually, the tree has been told you're going to be this big, and we go off that, so we make the map bigger somehow. That is going to be an issue at some point. For now, I'm just going to readjust my coordinates. So basically, in case you didn't understand what happened there, oops, let me actually comment this out so that it runs properly. Basically, we've got 8 by 8 here, and I told it to put a block out here. And because we're using quad trees, which you can see there's that bounding, you can kind of see that small little red outline there. It's going to try to figure this out. And so it probably ended up at this pixel here. And then it said, well, I've gone down as far as I can, and I can't get here. Because it's a quad tree. It's not, the way we set up our quad tree, it's not capable of getting any bigger. In fact, what we'd probably have to do if we wanted that quad tree to be bigger is we'd probably actually have to create another quad tree, slightly larger, and then reset all those pixels. Because the quads are going to be different if you resize it. Anyway. In that case, I'm just going to make this more like 5 by 5. And maybe I will also make this a little bit bigger because 8 by 8 is kind of small. Okay. There we go. And now you can see that the quad trees have actually gone in there. That's mildly annoying, but that's okay. So we've got a wall. All right. Let me actually, I want to set up an actual wall. Okay. 6, 7, 8, 9, 10, 11. Okay, there's our wall. Now, anytime in pathfinding, you've got two things that you want to do. See, now that we've actually got the map and all that set up, we can actually do things. You want to get from a goal or from a start to a destination. Start to goal. So what I want to do is I want to create a start. And that means I have to set a type for it. Because then our map knows how to draw it. And then start. Let's make the start be green. And the end be red. All right. And let's put our start here. This is going to be what? 0, 1, 2, 3, 4, 5, 6, 7, 8. So this is 8. And then this is 2. So 2, 8. Map.tree.set 2, 8. This is going to be start. You notice I've been putting 1 in here. I could have also put wall because we have a nice constant for it. Okay, there's our start. Let's put our goal here. This is also 8, but it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's put it at 10, 8. 10, 8, and we're going to put end. Cool. Now we have a start. Now we have an end. How do we get between them? How do I tell this? If I wanted a path that moved between the green one to the red one without going through a wall, because the wall is solid, how do I do that? Well, there's a couple things. There's a couple ways that we can do that. One of them is called the A-star algorithm. Now, A-star is a kind of a derivative of Dijkstra's algorithm. Dijkstra's algorithm is designed for graphs and finding paths, the quickest path between 2 points in a graph. And so you might be thinking, well, this is not a graph, but it is. Because any square grid like this, or grid of squares, is a graph where every single element has connections to the 4 elements around it. So if I were to draw little connections between every single one of these squares to its neighbor, it'd be a graph. It's a very dense graph, but it's still a graph. So the whole idea of Dijkstra's algorithm, well, I'll draw it. Might as well. And this may not be the actual 100% true to life Dijkstra's algorithm, but this is my understanding of it. So let's say we got some nodes. Okay. Node and node. Now, we're used to trees where these all have a hierarchy. Imagine this is more of a distributed graph where some of these are all cities. Some of them can go to others. Some of them cannot. So for example, this one has no road here. So if we're here and we're trying to get to this node, what is the quickest path there? Then what you do is you put weights on them. So you say, okay, this is 5. This one is 6. This maybe is 2. Maybe this is a freeway. This is 12. This is a really mountain pass. Notice it's not windy like a road. It doesn't have to be because I don't actually care what the road looks like at this point. I just care that it takes a certain length of time to go between it. So if I want to actually go from this point to this point, what is the quickest path to do that? Well, if we look at it on the graph, we can see, well, it's kind of, oops. You start here, you go up here, you go here, then you go here, right? That's a path of cost 9. If I go the other way, that's 5, 9, plus 12. Maybe it's a nicer drive because of the 12, but it's going to take longer. So it kind of depends on what you're optimizing for. Now, algorithms like this is actually how a lot of mapping systems work. Like if you're doing Google Maps, it is much more complicated and has a lot more nodes and has a lot more pieces to it. But it's using a similar path like this or algorithm like this to determine how to get there. And so what you do in Dijkstra's algorithm is you have a start node, okay? And you color that and you say, okay, we're here. That is a cool color green. I like that. Then you look and you say, okay, let me look at all the paths that come off of this node. Every single one. Well, actually, you see I take the shortest one. That's not completely true. You don't look at every single one. You look at the shortest one first. So we look at this too. And in doing so, we say, okay, we're done with this node. We're not done with it, I guess, because we have to handle all paths. We go here and we say, okay, now we are here. What's the shortest node off of here? Now, there's 2 5s, right? But this one is actually a 7 path, and this one is a 5 path, so we're going to check this one first. Okay, we go to this node now, and in doing so, we've collapsed all the paths here, so we say we're done. We finished that node. It's no longer something we care about. Now, from here, we say, okay, what's the shortest path we have? Well, it's a 4. It kind of depends whether or not the shortest path is what's the shortest cumulative path or what's the shortest path on the node. If we're doing cumulative path, it would be this 6 and 5. And we'd say, oh, 6 or 2 and 5, that's 7. Okay, so that's going to be shorter than this 9. So we say, okay, let's take a look at that 5. And we open up this node. And oops. And then we say, okay, well, that's 7. That's going to go up to 9. We've got this 6 here. That'll only go to 8. So what happens if we take this path to here? And in doing so, we've now completed this node. We don't need to look at these anymore. We get here and we say, oh, we already have a cheaper path that gets to that node, so we don't need to worry about that. But now we've got this 5 from this 4 and this 2, 5, 2, which are actually equivalent. But this one got pushed onto the stack first. So we're going to take a look at this one. We're going to go to this node here. And now we've got a 9 path. And this node is now done. Okay, well, that 12 is pretty high. So now we're going to take a look at the next 2, 2, 5, 2. In doing so, whoops, we open up this node. And then we close this node because we finished all the connections to it. This happens to be our goal node, so we're done. We don't need to bother looking at the next path because we've already found the shortest path. If there was a shorter path to take, we would have found it already because we would have processed that node first. So basically, Dijkstra's algorithm guarantees that you have found the shortest path. This is also used for networking. So if you've got a bunch of computers connected to each other via connections of various speeds, then this algorithm, Dijkstra's algorithm, can be used to determine the quickest path between two computers. In this case, that path, let me use actually a nicer color, is going to be these nodes to get to the goal. And we know that because we can backtrace at that point and see where we came from. So that is kind of how that algorithm works. We basically look at the nodes in the graph and slowly branch out in every direction, because you might have noticed we went from this 6, right? Why would we do that? Well, we didn't know. Maybe it's a quicker path, right? Maybe this is a 2 and that's actually a quicker path than this 5. We don't know. And so we have to check every single path until we get to the goal node, because technically the computer doesn't see the graph like this. The computer doesn't actually know where the goal node is, really. It kind of does, but it doesn't really know how to get there. And so it has to go through every single node. Now, how do we do this in a grid? Well, let's say that we put a grid. Okay, I'm going to do kind of a small grid, just because I don't want to draw too much on it. Okay, so we got our grid. This is a terrible grid. But basically, we want to get from here to here, and there's a wall in the way. So there's this wall. Well, what we do is we look and we'd say, what of these two nodes, which one is closer? Well, this one is. Okay, actually, let me put this in blue. Okay, so then we'd go to this node. And we'd say, okay, because that node is, we ignore the barriers. And we just say, what is the closest distance node? Okay, that one is 3. Cool, so now we have these two nodes. Which one is further away? Well, this one is 1, 2, 3, 4, 5. And this one is 1, 2, 3, 4. So we go with this one, right? And then this one's closer. Okay, and then this one's closer. And this one's closer in there. But you can see we've moved around the obstacle. If this was black, then we would now reach a dead end. And we'd have to go the other way and go around. So this is the same exact thing we can do on a rectangular grid that we can do with Dijkstra's algorithm. And that's just because a grid is a graph. So we come back here. How does that help us? Well, if we look at this here, that's basically what we do. We start from this point and we look at all of its children. And we say, well, what's the closest one? Well, it's this one, right? Okay, now we have all these children to look at. What's the closest one? This one. And then we start branching out on either side, and eventually we get around the wall, and immediately it makes a path here. So what we're going to do is I want to show you kind of how that works. So let's create a button, and that button is basically going to allow us to take a step along the path and compute another step. So button ID equals take step. And then we're going to hook it up in our index, not our index, our script. Okay, so we're going to come in here and we're going to say document.getElement by ID, take step, add event listener, click. And so what happens when we click on this, we're going to determine that. But basically, as soon as we click it, we're probably going to modify the tree. So we're going to draw the map and re-render. That's basically what it's going to do for now. As soon as we click this button, we draw the map and we re-render. That's actually a very efficient 43 out of how many elements we have on here. So yeah, it's just going to re-render for now. Now what I want to do, okay, is I want to be able to look and keep a tree, okay, or a list of nodes that I need to look at. So that's going to start off with my goal node, okay? Nodes to look at. So that's going to start off, I'm going to say x is 2, y is 8. Cool. So when we take a step, the first thing we're going to do is we're going to look at our first node. What's the first node we got to look at? So we're going to say node, equals nodes to look at dot. There's a couple ways we can handle this. The way we would want to do this is basically when you process a node, you add its children onto a queue. Thing is, this needs to be a priority queue because we need to handle these children into a queue, but we want them in priority order of their cheapest path. Okay? And so that's how we need to add them into the queue. So we don't actually have a priority queue right now, and so I'm not actually going to build that yet because I want to show you what happens without a priority queue. This seems awfully familiar, me saying that, so maybe I feel like I've gone over this before. Who knows? We're doing it again. This is what I want to talk about today, and so that's what we're talking about. So a queue is a first in, first out. So you push from the back, but then you shift off the end. So you shift off the front. This is not a push pop because that's a stack. And so what we're going to do is we're going to shift. And what shift does is it removes the first element in the array. So here's our node. What we got to do then is we got to look at all of its... Well, first of all, we got to check if it's the goal, right? So if... Well, maybe we do that later. Yeah, let's do that later. That's the end. Once we get that, we're done. So we're nowhere near there. We got to get all of its children. Okay, so let's do that. Let's say, okay, children equals, and I'm just going to make another little list here. This is going to be node.x minus 1. And then this is the child to the left. Child to the top is going to be node.x. We're not doing diagonal here. Node.y minus 1. You can do diagonal actually pretty easily. You just have more children in it. Which, you know, completely legitimate. This is going to be the right, and this is going to be down. Problem is, these children might be off the map, right? Because our map is not the biggest thing in the world. So what we want to do is we want to filter them. So I'm just going to put a dot filter on the end here because I can do that. And I'm going to say it's only true if the element dot x is greater than or equal to 0, and the element dot x is less than 400 divided by 25. Why 400 divided by 25? Because that's how many cells we have. Why less than? Because we index at 0. So 400 divided by 25 is, I believe, 16. I may be wrong about that. But it doesn't go to 16. It goes to 15. It's 0 to 15, and so that's why we have that less than. And element.y is greater than or equal to 0, and element.y is less than or equal to 400 divided by 25. Actually, you know what? I can just return this because that's my child, my children, right? Let's just console log that for now. Let's see what we get. So we go here, take step. Y is not defined, 46. See, this is why we test it very quickly. 46. Oh, dot. There we go. We find these issues. Okay, y is not defined on 48. Probably the same issue. Yes, it is. Should be a dot instead of a minus. Okay, now we have our children. x1, y8, that makes sense. x2, y7, x3, y8, x2, y9. So these are the 4 children here. So what I want to do then is I'm going to pop them onto my nodes to look at. And I'm actually going to give them a special color. So let's say look at is 4, because I want to show these on the map. And this is going to be, let's see, yellow, which is red green, I believe. So what I'm going to do is I'm going to loop through my children. Oops. Const child of children. And I'm actually going to set it on the map. This is not something we do normally. If we were doing a Pathfind algorithm normally, we just run it and then we send the path back. However, I want to visualize this. So I'm going to say map.tree.set child.x, child.y, look at. Okay. Now I come here, take step, and you can see these all get set yellow. These are all now on the queue to be looked at. We're going to say, okay, now we're going to look at these. This one is now done. It's complete. So I'm actually going to mark it as a darker green. So let's say const complete equals 5. Complete. You can see how easy this is now. I can just add these cells into my map very easily. The darker green, let's say like 90. because I got to set this now. I'm going to say map.tree.set node.x, node.y, complete. Come here, take step. That changes to that darker green because, yeah, we're done. We finished it. We processed it. Now we actually got to push all 4 of these onto the queue. So in the same time that we're doing this, we're actually putting nodes to look at dot push child. And so now if I get here and I take a step, I should be able to take another step. Oh, this got set. So that's a problem because now you can see we're actually just going to do stuff like this and it's not going to be super great. I don't want to, if I take a step and I take another step, I don't want this going back on the queue because I've already processed it. So I do actually need a list of elements that I've processed. Process nodes equals empty. And we're going to push this on that. Process nodes dot push node. Now, when I'm actually setting these and looking at these, I need to filter them by that as well. So what I need to do is, let's see here. I could do it on this filter actually. So let's see. Do I want to do that? No, I'll just do a second filter because you can filter twice. This is actually what these why these array functions are really nice in this case, because you can utilize them and chain them in this manner. So you can see I've done one filter which just verifies that they're on the map. This filter is going to verify whether or not they're actually in process nodes. I have not found the path yet. I am still in the process of finding the path. The path is going to be hard to find, but this is hopefully going to be an A-star algorithm. You know, once we get there, it's not actually that complicated. I just want to make sure that it's explained. Yeah, it's right there. It's right there. I can see it. You just look. You just go over there, right? Easy. All I have to do is just get a bunch of interns sitting in cubicles, and every time someone needs to compute a path on my map, I just send them an email that says, hey, compute this path, and then they're just going to plug in the numbers here, and then they're going to send it back to the program via email. I think that would actually work really well. And the only issue, honestly, that might be cost effective. The only issue is that it'll take a long time. Yeah, because the interns, like, they're gonna go on a coffee break, and then the emails will start piling up, and then they'll be like, "Oh no, I'm not being paid." Pay your interns, folks. Yeah, the intern will just come to me, and they'll be like, "Hey, I can't find the path. What do I do here?" Okay. So let's see. Let's filter this down. So we've got our X and Y in process nodes. We got to find out if element is in there. And so there's a couple ways we could do that. The cheapest, or not the cheapest, in time it's actually kind of expensive, but this is just the simplest way to do it. Yeah, if you're pro questions with your interns, then they will learn and they'll get better. That's what I found. They are there to be taught what not to do. So let's see. What I'm gonna do is I'm just gonna do this like a really dumb way, and then I'll fix it later. I'm just gonna loop over processed process nodes, and then I'm just gonna do a check. Again, there's better ways to do this, but this is how I'm gonna handle it. If process.x equals element.x and process.y with element.y, found equals true, and we break. So if we found it, well, actually we could just return not found, right? Because if it wasn't found, then we know that it didn't exist in process, so it's a valid neighbor. I still have that leftover attitude of no one answered my questions and I was an intern. I'm sorry. Being an intern is sometimes very rough because people, especially if they're busy, they don't have time to answer your questions. I'm sorry you had to go through that. I have had similar experiences when I was an intern a very long time ago. That's why I definitely try my best to provide something better for the people that come after, because that's all we can do. Anyway, so now we take our step, okay. We take our next step, and now you can see this one does not become another child on the queue. Okay, we take a step. And you can notice these are actually just going in order of when they were added. Um, Oh, here's a problem. That also wasn't valid. Because that's a wall. That's an obstacle. We don't want that on the queue. That shouldn't be there. So we should actually do something here too. We should say, okay, value equals tree.get, oops, map.tree. .get element.x element.y. And then we should say, oh, you know, oops, this should not have this on it. If value equals wall, then return false. If this is a wall, then this is not a valid element, and we shouldn't have that in there. Let me try that again. Step, 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 step. Okay. I feel like it's still adding these neighbors in somehow. Because you can see, like, sometimes I click this button, like here, 1, 2, 3, and if I click it again, it doesn't, I feel like it's still grabbing this somehow. Huh. I don't know why that would be happening. We're building a pathfinding algorithm because it's fun. It's good practice. You know, it teaches us. Basically, this is it's a not super complicated algorithm, but it is kind of interesting, and there's a couple little gotchas that you have to worry about. For example, why the hell did that happen? So let's see. I take a step. Okay, I've got these children. 1, 8, 2, 7. These look good. Next step, I've got 3 children, and that's fine. 0, 8, right, which is this one. 1, 7, and 1, 9. Okay? I should actually log the node we're working on too. That'd be a good one. Processing node. Because at some point we're getting one of these nodes that doesn't do anything, and I'm kind of wondering why. Okay, so we go here, we go here, we go here, and then what's the next node? 1, 7. 1, 7. Wait, 1, 7 is going to be this one. We already processed that though. Annoying. We processed. Okay, 2, 8, 1, 8, 2, 7. Yeah, we processed 1, 7 already. So now we have a problem. Is we got a child added onto our list that was already there. Okay, so now let's make this more complicated. Because now we have to look over whether it's processed. Whoops. But we also have to determine if it is already on our list of nodes. Because if it's already on our list of nodes, we don't need to add it again. So if, I'm going to change this to if not found, return false. Okay. And then I'm just going to come down here. And what did I call this? Nodes to look at. Node of nodes to look at. That's the wrong one. All right, basically same idea as this one because they're the same exact data structure, and I think that will fix that issue. Let's try it. So 1, 2, oh, it didn't add anything. Because found was already, yep. Yep, I gotta reset this. Found, if not, oh, if found, return false, not if not found. Because if we didn't find it, yeah, that's good. Okay. Okay, we go around here. We go around here. Okay, there. And then the next one's up there rather than that one again. Cool. So now, if we just keep stepping, you can see this basically goes around in a very, very large circle. Or kind of almost like a triangle. You see, and it's slowly inching its way closer. That's funny. I must have some error in there. What is this? Processing. That's some trees. Okay. Oh, yeah, the tree screwed up because somehow I tried to add something that was off the screen. We'll have to fix that as well. Okay. Comes down here. And you can see we're getting closer. But it's taking a really long time. Oh, and then it got added into the queue. So as soon as we process everything else, there we go. Now we found it. And I know everything's green now, but basically now we found this thing. So that'd be nice to have as an end step, right? That we found it. It'd also be nice if this could be a little more optimized because this is really friggin' slow right now. And I have to click a lot. So the biggest issue is that we're just adding children and it's just going in an expanding circle. And that will work. Eventually it will find a path. But it'd be nice if that was a little more directed. So if we had something where we said, okay, you know, let's try to make better choices about what path we're looking at. So that is where the priority queue comes in. So if we can actually determine what is the cost to get from this node to the other node, and that cumulative cost, then we know the cheapest item we should look at next. Why would we look at the cheapest item next? Well, we don't have any other basics to go off of, and the cheapest item might be the goal. So what we want to do then, there's two ways to go about it. In Dijkstra's here, we had what is the cheapest path to get here. And that's a way we can do it. But in a grid, a better algorithm to check is how far away are we from the goal. Okay? So if we've got, let me reset this. If we've got a cell here and we want to find the distance between any cell and any other cell, there's actually a very specific mathematical formula for that. And that is because that is the hypotenuse right there. So if you look, if I go here, that is technically a triangle, or over here, that's technically can be a right triangle, with the hypotenuse being the distance between the 2 points. Math. So how do we figure that out? Well, let me actually create a formula for that. Function distance between points. X, Y, X2, Y2. So this is not super complicated. But actually, you know what? Let's derive it a little bit, right? So what is, you have your c squared, whoops, let me just make a comment. So c squared equals a squared plus b squared, right? That is the formula for the hypotenuse. The c squared equals a squared plus b squared. If you don't believe me, look it up. So the first thing we need to do is we need to actually, we're trying to find c, which means we need to take the square root of both sides in order to get that times 2 off. So then we get c equals square root of a to the 2 plus b to the 2. So this is the formula for finding the length of the hypotenuse between 2 points, or the distance between 2 points. It's not super complicated if you know your geometry. But I guess this might be trig, actually. This is why math is kind of useful when you're dealing with stuff like, especially gaming when programming, because there's a lot of algorithms in it. So I'm just going to say, okay, math.square root of math.power. Math.power is how we do the exponents. And so what is a then and what is b? That's a good question. So let's say we have our triangle here, right? And we have this, and we have this, but it's on a grid. So it's on an x and y plane like this. We need these two lengths because these two lengths squared plus each other, and then the root is this length. Well, this length is x minus x, right? It's this x minus this x. Sorry, I know I just said the same thing again. But basically, it's x minus x2. Okay. And this still does actually work if you flip those coordinates, because if you take the power, a positive power of anything, well, actually, yeah, if you take the positive or an even power of anything, it becomes even. And that becomes important because square root on a negative number is not good. So you don't want that because it's imaginary. So this math.power ensures that we never put a negative number in here. And same thing, we have y minus y2. So this is the formula for getting the distance between 2 points. Just trust me on it. This is how it works. And I've used this. I keep this and just put it in a bunch of places whenever I need it, because you'd be surprised how often you need this exact thing. This is 2 points. Anyway, let's take a look at the distance between our points here. So if we look at our node, or actually for our children, okay, when we're pushing them into here, distance is going to be distance between points, child.x, child.y, and then our goal x and goal y, which is 10 and 8. Okay, so now we have our distance. Log child distance. Let's just log that to make sure that works. Okay. Take step. Okay. So now you can see 9, 8, 9. These two are identical because they're at the top and bottom here. This one's the furthest away. The logical next step, if we're looking for the smallest one, is going to be this one. But if we take a step, it's going to be the first element that was added into the queue, which is 9. Priority queues, right? So what I'm going to do then is I actually want to implement a priority queue. And because I don't think JavaScript has one, let's check. JavaScript priority queue. If it has one, I'd rather use that. Okay, implementation of priority queue in JavaScript. The fact that like people are talking about, oh, how do you do this? How do you do this? Blah, blah, blah. Means it tells me it doesn't exist. Okay, so let's make that priority queue. So if we're dealing with a priority queue, one thing we could do is we could implement it the way queues are actually implemented with nodes, similar to how we did the tree. However, a hash map works actually just as well, because what you do with the hash map then is you build the hash map with the key being the priority and the value being an array of values that map that priority. If you add multiple values into a priority queue with the same priority, then it's kind of a crapshoot as to which one you're going to get out. There's really no guarantee, so you want to try to avoid that. Or if you don't care. So for example, in this particular case, these two would be the same priority. I don't actually care which one I get first. It doesn't really matter. So the idea then here is we just use a hash map, but every time we insert a new element, we sort the keys of the hash map and then reassemble the hash map based on that sorted order. Or actually, we might not even need to reassemble the hash map. We could just keep the hash map with those keys, but keep the sorted key array. This may not be the most efficient way to do a priority queue. So this is the other reason why we might want to do a pathfinding algorithm, because it leads us to interesting stuff like this. Priority queue. So we're going to have a constructor, and this is just going to say, okay, this dot map is empty, this dot key list is empty. Okay. Now we're going to have some similar methods. We're going to have push, and then we're going to have, well, it's a queue. So actually, technically, these would be NQ and DQ, because you don't use push for a queue because it's not actually a push. So NQ with value and priority. Okay. So if this dot map priority, so the priority already exists in the map. We're just going to say this dot map priority dot push value. Important note on that: if the key already exists in the priority queue, we do not need to regenerate our key list or reorder it, because it's already sorted and we didn't add another key. We only need to modify or resort the key list when we add a new key. So otherwise, this dot map priority equals an array containing the value, because we got to start with an array. Then we got to resort our keys. Okay. So what we're going to say is, all right, this dot key list equals object dot keys this dot map, and that's just going to get us all the priorities, and now we sort them. And actually, I probably can just say this dot key list dot sort. Why am I not saying object dot keys this dot map dot sort? I don't know what this. I'm not sure this actually returns. Oh, returns a reference to the same array. Oh, so I could totally do that then. Never mind. So this should be a simple priority queue, hopefully. Let's do this. Let's just have a debug print function that just console logs the map and the key list, just so that we can verify it's doing what we want. Next thing is the DQ. The DQ should find the lowest priority element on the list and pop the value out of it. If this value is empty, then it should then delete itself. So lowest priority equals this dot key list 0. Also, we should check to see if we actually have a key list. Dot key list dot length. If it is equal to 0, just return null. Because what else? The queue is empty. There's nothing there. So our lowest priority, let's just say const element equals this dot map lowest priority dot pop. Actually, let's do shift. So let's just treat this like a regular queue, first in, first out. Again, it doesn't actually matter. In this case, we could use pop, and that'd be totally fine. But shift just make sure that there's some churn of things. If this dot map lowest priority dot length equals 0, okay, then we actually need to delete it. This dot map lowest priority. That is what this will do. The delete should actually just set this to undefined. And then we're actually going to say this dot key list dot shift. So we're going to shift the key. Here we actually looked at it. We just said, okay, what is our lowest key? What is our lowest priority? In this case, we're actually removing it. We don't want to remove it until that element is empty, or that list is empty though. So no idea if this is going to work. It holds up, like theoretically, but I may have fucked something up. So let's see. Now, instead of our nodes to look at, we're actually going to say nodes to look at is going to be a new priority. Whoops. Priority queue. Okay. And then we're going to say nodes to look at dot enqueue our object. And the priority is going to be distance. I could set any priority here. The fact that this is the very first element means that it actually should be fine to have a priority of 0 because the queue can't look over anything, but this is just for, you know, it feels right. Between 2.8 and 10.8. Eventually, I want to make these not magic numbers. Node to look at. So now this is going to be DQ. And this down here is going to be NQ with the distance. I'm kind of curious to see what happens if I just do this. Priority queue is not defined. That makes sense because I haven't put it in here. Source equals priority JS. There we go. Okay. Step. Oh, okay. Well, that broke. Script.js 16s set node.x node.y. So the DQ busted. Something went wrong there. Well, cool. Let's see. First of all, I bet it DQ'd null. That would be my suspicion. Let's take a look. Nodes to look at that print. Because this is our debug function to actually get some data printed out. What do we get? Okay, we do get 8 and 8. So when I take a step, processing undefined, somehow DQ is giving me an undefined. Oh, I never returned the element. That would be why. I was like, if it was empty, it should be returning null. No, that's why. Okay. Take step. Nodes to look at is not iteratable, probably because I'm trying to iterate over it somewhere. 92. I'm still treating it like... Yeah, there we go. And, you know, in this case, I probably need a contains then. Contains. This is actually then technically a priority queue that's also a set, which is kind of interesting. Contains, let's just use a compare function. And so then I'm just going to loop over my entire list here. I'm going to say object dot values this dot map, or not map actually, for each value. Compare function. I don't like that. I'm going to do it as a for each, or a loop, because I just like that a little better. If compare function value return true, and then otherwise return false. So this is a simple little function, just loops over all the values in my map and runs them through this comparison function. Why do I do that? Because priority queue doesn't know necessarily we're dealing with coordinates. So I don't want to actually build the comparison here. So now what I can say is if, or rather I can say found equals nodes to look at dot contains, okay, and then I'm just gonna, this is probably not a great way of doing this, but I'm okay with it. And then I'm gonna just grab this, return this. So now this function will get called, oops, on every single value. And am I looking? Yeah, node is fine. This will get called on every single element in our queue, and then it'll determine if it was actually existed there or not. Yeah, okay, cool. So we got those 4 nodes. This should be the next node now. And it is. Now this should be the next node. Okay. Now it's going to be either one of these. Okay. And now I'm not complete. It might do these and it might do this. Let's see what it does. Okay. There we go. Okay, now you can see it got up there because this was actually getting too far away and these were closer. So it checks those. And now what is it doing? Okay, it's going there, here. Okay. And now you can see it does that little step pattern. So that is much more efficient, honestly. Like, that is much more efficient than looking at the whole fucking thing. So what I want to do here then, I kind of want to actually keep that start and end visible. So I'm actually just going to pop this back in here and say, even if you unset these values, set them back to the start and the end, just because that's kind of nice to have. Okay, so there we go. Perfect. Now, if I keep going, you notice it also keeps like checking closeness. So I need to actually be able to tell the algorithm it's done, that it found where it's looking for. So what we're going to say is, okay, if node.x, node.x equals 10 and node.y equals 8, complete equals true. Okay, so now I want to do let complete equals false, and then at the very top here, if complete, return. So basically this is just a flag that says, hey, if we already found the goal, don't keep going. There's no point. So now I take a couple steps here, and now it won't move. It won't keep going past this. Yeah, every possible path. No, that's legit. Choose the one with the least distance. Well, the thing is, if I compute every possible path and choose the one with the least distance, that's going to go straight through the wall. That's the problem, because this is actually the path with least distance. The important thing is I actually want the path of least distance that doesn't go around obstacles, right? So yeah, that's, otherwise, yeah, it'd just be check every single possible path and just get that one. That's actually pretty easy to do. And you're right. Even on a map this size, it wouldn't take that. Anyway, no, I get that. I understand that. But you know, the engineer in me can't help but say, actually, doing that would. Sorry, I'm an asshole sometimes. Yeah. So this is basically a star. Okay. The other thing is maybe we actually want to know what this path is, right? That could be kind of useful. So that involves a little bit more data. That involves us to knowing where we came from. Okay. So to start off then, I'm actually going to have a parent object on here. Okay. And so this one is null because that's our starting point. But every single one of these children now, their parent, oops, is going to be the node that spawned them. And the reason I want that is because once I get to that goal node, that's in the wrong spot, I can walk back the parent. So as soon as I get to complete equals true, I can start from my node. I know this is the goal node, and I know what its parent was. So I can say, let's walk back, oops, and we're going to loop while current is not null. Null. And then we're going to say current equals current.parent, because if we walk back our parent, eventually it's going to be complete. Or it's going to be null, because our very first one was null. And then I'm just going to do a map.tree.set. Map.tree.set. This is going to be current.x, current.y. And I actually need a color for this. Const path equals 6. It works for every type of program, and you don't need to optimize. Just run everything off 3 data centers. It's true. You're not wrong. And funnily enough, that's actually what Stadia was trying to do. They were like, hey, we know our little console that we've given you does not have the computing power to play these games. But you know what does? A GCP data center. And so they were just hoping on the bandwidth being good enough that you could send your commands to their rendering engine in the cloud. And it would do that rendering, that really complicated stuff, and then send you back the picture. And it did actually work from what I understand. It's just, nobody actually wanted to play any of their games. Or maybe people did want to play their games and they just decided to shut it down anyway. That would not surprise me entirely. Anyway, I'm going to make the path blue. I don't think we've used blue yet. But yeah, sometimes if you want to fix something, you could do a really complicated, clever algorithm, or you could just throw more power at it, right? That's why if you're doing something, you're saying, wow, this is going to be really complicated to do on the client because we don't know if the customer's computer can handle it because we have no control over that. You throw it to the server because you know how you can always make your servers more powerful, and then you just finish and send that image back up. I've seen people do it. Let's see, path. Let's do that. So hopefully as soon as we finish this, it should outline that path in blue. Nope, it fails. Can I read properties of null x because current something? Oh, because current is probably null. That's why. This actually needs to be here because we don't want to reset our current until after we process it. I'm sorry. I will make a better attempt to pretend the jokes are humorous. No, they're actually pretty good. I appreciate the humor. Okay, let's go here. There we go. Now you can see that blue path. There we go. We can throw away all the rest of the nodes. We get that path. Cool. Honestly, that's a good point. It is hard to tell sometimes what the jokes are because I've been doing this a while and I've heard some really bad ideas sometimes. Like I've legitimately had someone ask me why we were doing browser testing. They said, why do we need to test against multiple different kinds of browsers? And I said, well, our users utilize multiple different kinds of browsers and we'd like to make sure it works. And they said, yeah, but this internal testing framework that this team built and wants us to use, it doesn't handle multiple browsers. And if that really was the case, wouldn't they have made it handle multiple browsers? And I didn't really know how to respond to that because I was a junior engineer. Nowadays, I would say, sure, if you as a manager think we don't need tests on this browser, I'm cool with that. I subconsciously rule out it being taken seriously because it's just that stupid. No, I think that's kind of the point, is that there are some people who don't actually understand how any of this works that come up with really bad ideas. I could see going to some VP who doesn't know tech very well and saying, yeah, the reason this is taking a really long time is because we need to optimize the algorithm. And they're saying, well, just build another data center. Like, why are we taking this many? Like, this needs to be done, last month. Why don't we just put another data center in? And then as soon as you're running a data center that costs $100 million a year or a month in some cases, and they're just like, yeah, change the color of the database. Exactly. Someone at some point said, you wouldn't go to your mechanic and while he's changing your oil, say, hey, also, could you make this an electric car while you're at it? But someone will come up to a developer on a site and be like, oh yeah, can you just totally change the way this form works? That should be easy, right? It's just a couple of fields. And you're looking at it and you're like, yeah, but those fields are required for this particular process, so we still need those fields. I can't just get rid of them. We have to go through a deprecation process and change all this stuff. And yeah, I think they just don't get how this works, but they think they do. And that's kind of the problem. Like I've had managers who don't know what I do and they know they don't know what I do and they're cool. They're just like, yeah, I gave you this ticket, you did this ticket, we're good. But if they don't know what you're doing, but they think they know what you're doing, that's when the problem starts showing up, at least in my opinion. So the next thing I want to do here, now that I've got this, let's actually push this path.push current. And actually this should be before this as well. So now that we've got this here, this is on take step, right? I'm doing every time I click that button. It'd be kind of nice if we had the ability to just run this, right? And just have a single button that computed the whole path and ran it. I'd really like that anyway. So I'm going to make a new button. And I'm just going to call it run. And we're going to go back to our script here. And let's add in a hook for it. Document.get element by ID. Run.add event listener. Click. So then at this point, what I want to do is I kind of want to algorithmize, whatever. These process nodes and complete and all this other stuff. The complete isn't really that important, honestly. So I really just need process nodes and kind of this entire thing here, nodes to look at DQ. And I want to grab all this and pop that in here. I do want it to run as a loop though. So while nodes to look at dot, and now I need a function to figure out how many elements are in my priority queue. Length, return. Actually, I should. That's going to be kind of hard, isn't it? Oh yeah, and also this doesn't work. Because the values are actually going to be a loop. So what I need to do, I'm just realizing this because these are all arrays. And that probably screwed us up at some point. Value of values. There we go. I need something like this, and I need to be able to count them, right? Because that's... No, you know what? I'm just going to maintain a count. Every time we enqueue something, the count goes up. Every time we dequeue something, the count goes down. Totally fine. Normally, you want to make sure that you put in some checks to make sure that this stays in sync with your actual data. The data is simple enough. It's not going to go out of sync too much. Or at all, hopefully. Otherwise, I'd actually have to do the same loop and just count up all the values because we are using an object of arrays, which is kind of awful. Anyway, dot length is above 0. Why do we have this while loop like that? This dot length is above 0 because let's say that at some point I put this in a box. At some point I am going to run out of nodes, or I put this in a box. I will run out of nodes eventually, right? I am going to run out, and that is going to be a problem because as soon as I run out, what's going to happen? If I do an infinite while loop until I find the goal, it's going to loop forever if it can never find the goal. So you want to give it that case that if you run out of nodes to process, the goal can never be reached, because that could happen. So let's see, process nodes, all that stuff. That is great. Nodes to look at also needs to be down here though. Nodes to look at and then queue, etc. I'm just going to pop this. I know I'm duplicating a ton of code here, but I don't really want to rewrite that code to work that way. And then this draw map set. Oh, this is in there twice. I'm actually going to pull this to the end of the loop. So now what this is going to do is I'm leaving my map tree sets in there because it's kind of interesting for the path and all that. And then actually here I need to break because I'm done with the loop. I found the goal. I'm just basically doing this now in a loop. So it sets all the same data up, but it's going to do it very quickly because I don't have to keep clicking the button. At least that's the hope. So if I run, there we go. Now, I might want at some point to actually be able to modify these walls. I kind of want to be able to click and have a wall appear or disappear. Only issue I have with that is if I click my map, how the hell do I figure out what cell this is? Like, I could do that computation, but it's almost be better if the map did that computation, right? So I kind of want to put something on the map that lets me know or takes an X and Y coordinate and turns it into a grid coordinate. I think that'd be really useful. And then what I can do is I can actually put something on the canvas, wherever my canvas is. Canvas dot add event listener. This is a thing you can do with canvases. You can add event listeners onto them with click events, just like everything else. Click E. And what I think I need here is I need, oh god, I don't remember exactly which one is the best one. There's a bunch of different coordinate pairs on the event, so let's just see what we get here. Pointer event. Okay, so we've got client X, client Y, layer X, layer Y, offset X, offset Y. I think it might be the offset X and offset Y. I think that might be what we're actually looking for. So let's just pull that out. X as X, offset Y as Y equals E. Cool. Const.log, offset X, offset Y. Let's just double check. I want to go and click in the corner here. Oh, because I called them X and Y. And yeah, okay, fine. Okay, fine. Just make a div for each cell. Yeah, I mean, that would work, but then that kind of overrides the whole point of the map in general, because the whole point of the map is that it didn't need to do that. That's 2, 0. That's actually pretty, yeah, that's pretty close to 0, 0. And then this is down here. Oh, that's 400, 0. I messed something up there. Oh, because I did scream Y. That would be Y. No, not offset Y, just freaking Y. Okay, so now what I want to do is I want to go into my map and I want to give it a function that does that computation. Maybe, okay, that was sarcasm. Well, because some people do maps that way, right? And that was actually in the very early examples that we did, like the, not the comparison statements, the quad trees and the wavefront collapse. That is actually how we did that. So if I take a look at that, that was actually using, it wasn't, it was using table cells, but it's kind of the similar thing, right? It's using table rows and table cells. So again, that is something where someone may actually legitimately say that and be like, oh, yeah, that's a thing. That's a thing that we should totally do. And then they just go ahead and do it. Yeah. I'm gonna go up to my home and drop the okay, so let's see here. What, oh yeah, canvas object, random stuff. I already added a mouse move onto that. Wait, did I already add? Oh yeah, buttons, that's why. So I already added buttons on here. Okay, so let's just add a specific function on here. Get cell from, I don't know what I just did, from real. So get cell from real, what does that mean? Well, real is kind of like the real coordinates of the actual canvas. Cell is going to be the cells stuff. So the first thing we need to do is we need to offset it by the offset, right? So if our offset is here, well, here, then I don't want to necessarily, like I need to reset that back to 0 so I know what I'm clicking on. The problem is I don't remember if my offset gets positive or negative. This map offset X. Let me just do that. Oh no, I need to call it. So if I go in here and I call map dot get cell from real Y 2 a.m. Oh god, that is very early. So that means, are you in the UK or somewhere in Europe? I'd imagine if it's 2 a.m. right now, or maybe even no, that might even be UK. That's even further. 0. Okay, so if I go here, okay, it gets bigger. It gets bigger as it goes here. UK. Okay, that makes sense. Yeah, the time difference I'm sure makes makes a bit of a difference. Okay, so it goes negative and it goes positive as it goes this direction. That's fine then. So what I'm going to do then is I'm actually going to subtract it. You're not in the UK. Oh, so you would be, yeah, okay, so you're 2 hours further from the UK. That's what you were saying. It's 0:30. I thought you'd actually just check the clock and be like, oh, it's not actually 2 a.m. Okay, so somewhere like my geography of those time zones is not super amazing, but I'm gonna guess somewhere in like southern. Oh, it's 1:30. Okay. Oh, so you're probably then in like somewhere in like Germany, maybe Switzerland, France. I don't know. I'm just spitballing. Let's see. So I'm gonna take the x is gonna be. We want to take our actual x minus this map offset. And then we want to divide that whole thing. Is it Germany? Well, I just, yeah. I am more familiar with Germany than I am France. Math dot floor. And then this whole thing is going to be divided by the cell size. And I think that should give us our grid. Because basically what we're doing is we're taking our coordinate, we're redirecting it to the origin, and then we're scaling it down by the cell size to figure out where we are, and then we're flooring it so that, because otherwise if you don't floor and you round, if you go and click halfway in this cell, it's actually going to be in the next cell, which is not what I want. I always want it to be in the cell I'm clicking on, so I have to floor to get down. And then the y is going to be something similar, except it's going to be with the map offset y. This actually doesn't fully work because we need to bring the zoom into effect. If we zoom in and out of the map, which we can actually do, then that does affect things because now the click is somewhere different. The cell size is slightly different. I'm not too worried about that right now. I'm just going to put in here, needs zoom handling. And then that will be a problem for me later. It'll probably be a problem for me later in like half an hour, but we'll see. And then let's just log this, console.log coordinates, and just see what we get. So I go here. I definitely should not be getting 13. Oh, cell size is not defined. I think because I called it start cell size. Yep. God knows why I did that, but okay. 0, 0, that's T. I don't want T, I want Y. Thank you. Okay, and this one is going to be 15, 15, 15. Now, if I move it, it's still 0, 0. That seems like that's still working. If I move the other direction, cool. So now I know when I click. So what I want to do, next and when I click up, okay, I want to actually set that to be a this is where things get tricky though, and I'll show you why in a minute. Why are you not using live server, Harry? I don't really like using the live server. I've seen some issues with it, and it's just not something I'm super familiar with. So, and also it's quick enough for me to just reload it. So it's just part of my workflow at this point. If you're comfortable with the live server, I would definitely recommend it. It's just not part of my workflow. You'll probably notice at some point a lot of things are not actually part of my workflow, so I just don't do them. Like I really don't use GitHub Copilot because it's just not part of my workflow. I've never worked with it. I want to at some point. I think things like this are valuable, but yeah, I definitely use it when I'm doing like a React thing. So if I'm doing like a React application or something that actually needs to build, I definitely use Vite or Webpack to do the hot reload for that. But if I'm just doing raw HTML or raw JavaScript HTML, I don't really do it too much. Anyway, map.tree.set. This is going to be chords.x, chords.y, wall. So now I can just build walls everywhere, hopefully. Oh, you know what? I actually need to re-render the map every time I do that. See, this would be why it might be nice to actually have a set method on the map, because then the map could know to re-render itself. Let's see. Okay, so now I can create some walls. Let's do this. Let's make some interesting walls here. And then let's run it. Okay, so it took a different path. What if I go here? Yeah, it takes a path there. You can see it went all the way over there. If I go all the way down like this, it's going to find that path. If I just cut that off completely, it's going to find a path here. Yeah. All right, so let's see. If we go all the way to the end here. Well, maybe not to the end. Oh, no, it's fine. It goes all the way up there. Oops. It did not like that. It had trouble with something here. Okay, so it went over here. Oops. And it had trouble with this. I wonder why. That's kind of interesting. So if I go down here, I kind of want to... Whoa. Let's investigate that for a little bit, because that's kind of weird. So if I step through this, when is it going to break? What is it actually processing when it breaks? Okay, it's going to get there soon, I think. Oh yeah, you can see it's actually trying to process a ton of... This is interesting. Why isn't it processing these? Because these seem like these should be cheaper than this. So I think there might be something wrong with the priority queue too. Okay, so down there. So we get to X2, Y15. That doesn't make sense. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That should exist, right? Like, that should absolutely exist in our tree. That's really strange. That's really strange. So something's wrong with the priority queue too. Because you might have noticed these never get processed, even though these should be cheaper to do. So what I almost want to do here is I'm actually going to put this in a box. Okay, so you go here. Let's just see if it processes everything. It does, but it processes them weirdly. Like, why is that? That's so interesting. Oops. So let's see. We take a step. We go here. We go here. So it's these ones, right? Let me just... Oh, no. That's not helpful. Whoa, what the hell is happening here? Okay. I probably should just save this wall configuration, honestly. But I want to see. So it's these back row ones, right? So these two never get processed, or they don't get processed until after the other ones do, which doesn't make sense because they should be closer to the goal, so the priority queue should put them first. All right. What I want to see is, like, what are those? Are they something weird about the way they get added? Okay, so take step. Okay, so when those got added, oh, I didn't log them. You know what I'm going to do is I'm actually going to log, no, not you. I think I'm going to log when I'm taking the step. I actually want to put in here the distance as well. Because I think that could be useful. Child distance. Because there's two things that could be going wrong here. One thing that could be going wrong is it could be not handling appropriately the actual distance, or it could be the priority queue is fucked up. It's probably the priority queue. But I wanted to see when I process these, it should tell me the distance. Okay, so these are a distance of 9, and these are a distance of, yeah, these are a distance of 10. So the fact that priority queue gave these before these indicates something's wrong there. So let's actually take up here, and we're just going to say nodes to look at .print. And I probably should just build these walls automatically into the system so I don't keep clicking here, but I'm not too concerned about that. Okay, so let's get here. So it picks this one, right? So at that point, what does our queue look like? We have 9, we have 9, 5, and we have 9, 2. Okay, and then we look at that. Okay, and that's what we've got. That's great. And our elements in here are 1, 7, and 1, 9. So we have these ones. And then we have 1, 6, and 1, 10, which are these ones. And that makes sense. So if I go one more step, it pops up here. So it's decided to process something with a distance of 10. Now, the interesting thing is that wasn't even... Oh, here it is. This is not in here. What? How am I getting a key that doesn't actually exist? Like, this is a key on here, right? It's there. But somehow something else got pushed in there. So then, okay, so we add this one. There's that one. Somehow we got this 10. That got added in there with this array that has... What is this, empty array? So we have an array here, but there's nothing in it. I am very suspicious of this. Like, just remarkably suspicious. Okay. So we're printing this right before we DQ it. So here's our 10. We're processing 10. Why is this in the front? Oh, because these are strings. That's why. That's dumb. So basically what happened here is these are all strings. And so they're not being ordered by numeric order. They're being ordered by alphabetical order. And 1 comes before 9 in the alphabet. Okay. Well, so that is a bug in the priority queue. Basically, then what that means, what we need to do is, yeah, right? Thanks, JavaScript. So when we're enqueuing this, I'm actually going to map these before sorting them. And I'm just going to return parse int on them. And I think that should do the trick. I think that'll fix it. Let's just try it now. Yeah. I'm glad that was a simple solution, didn't involve like some terrible, horrible nonsense. Oh, wow, okay. Cannot read properties of undefined read and shift. What? Oh, because I'm doing parse int on it. And they might be floats. Yeah, that's fun. Okay, well, let's try that again. Parse int. Take step, take step. Okay, so now that seems to be working okay. Let's just make sure that does what I expect it to be doing. It's still going for that 10. It's still sorting these weirdly. Why is it doing this? These are now strings. Or not strings, these are now numbers. So why are they being sorted all fucked up? You know what? Let's do this. Log, this.keylist, key, oops. Sort. Yeah, it's probably similar. So I'm going to sort it and then I'm going to log it after I sort it because I just want to know what is happening here. I'm doing good, man. How are you? It's good to see you. All right, let's see. So if I go here, I really only care about kind of when I'm around here. All right. So where is my... Okay, so here, this is sorted. That sorts appropriately. Okay, so I take another step. I take another step. All right. That's sorted. I enqueued that. This is 58. What am I actually looking? Oh, yeah, this is the print. Oh, yeah. TypeScript is a lot of fun. TypeScript is definitely a lot of fun. Processing. This is a distance. So we process that guy. So we take a step. We process this. That's cool. And now it doesn't sort it. That 10 doesn't get sorted appropriately. I wonder if the sort in JavaScript just doesn't know how to handle numbers. You know, I think that might be what we're happening here. But yeah, I'm glad you're learning TypeScript. I'm glad you're enjoying it. It's a great language. You know, I really like TypeScript a lot. And A minus B. This might not be right. I think it might be actually B minus A, but let's just see. No, that sorts appropriately. Okay, cool. All right, so there's our problem. It's just the JavaScript sort apparently doesn't know how to handle numbers, which is really dumb because you'd think if it was comparing numbers to numbers, it'd be smart enough to figure that out. Let's see what we get now. There we go. That's what I expect. Okay. Oh, and then it actually kind of seems like it's going off the edge of the world, which is fun. Oh, processing null. Yeah, so it's empty. Okay. Now if I do this, this is the original thing I was trying to fix. I was trying to figure out why this goes off the edge of the world. And then that was, okay, so we're down here. I want to clear this. Okay, it goes there, and I think the next one is going to be, nope, it goes up here. Wonderful. Okay, so we'll get 2 more of those. Oh, there we go. And, okay, now it goes off the edge. So this is 4 and 15. 4 and 15. Why is that causing issues with our tree? I keep opening Notepad++, and I don't want Notepad++. Why is that causing a problem with our tree? So what I want here, let's bring back our console log. And let's just see what we do here. Okay, this is going to be a lot of debug for a little bit, so I am definitely going to take a couple steps here until we get to that point of problematicness. Okay, so here we go. Take step. So what do we look at here? We're looking for 415, and it drops us down into 416 somehow. Oh, so this is an additional one. So these are all different. So we got 415, 415. 415 was fine. 515 was fine. And then we got to 416, and that wasn't fine. And I think the issue is then probably because we're still creating our children poorly here. Oh, because look at that. There's the equals. That's why it's overflowing the map on the bottom or on the top boundary. This one probably has that same issue. That's the problem. Okay, so now if I go like this and pull this down, I should be able to just run it. There we go. And now it gives me that path. All right, so what if I come over here? Cool. Cool. All right, so that is A-star pathfinding, essentially. That's what it looks like. That's how it works. This is not very efficient, honestly, because imagine if these things are tens of thousands of cells apart, and there's a lot of stuff in between them. There is something called, and this, again, we're into the section where we're doing something that I saw on YouTube, and I thought was cool. There is a potential way to do what we call line of sight pathing. And so that basically says, okay, I know that there's a wall here. Where's the nearest line that I can draw to that's the edge of that wall, right? Where's the edge of that wall? And I can get there. And then from there, I look and see, can I see my goal? Maybe I can, maybe I can't. But there's, and then that's a little complicated to do. Like, where do you find it? How do you find an edge of a wall? But there's actually kind of a thing that someone was doing, or I actually looked up on Wikipedia that I thought was kind of interesting. And that was, you can use a quad tree. Because the way our quad tree is set up, and this is kind of review for those of you who weren't here, if you might know that you might have noticed these red lines around here. Let me actually zoom in. These red lines, that's because we are actually using quad trees to render the map. This particular block is all empty, so that is represented by one single rectangle. And this is so that we don't have to actually have memory for every single cell in our map, because that'd be a lot for large maps. Instead, we group it all together, and contiguous blocks are all their own individual group. We can actually use a quad tree to do that kind of line of sight. So now here's how that would work. Let's say we have this block here, right? I know there's no obstacles in this block because this block has a value of 0 and it's in a quad tree. So I can tell that's a value of 0, which means I don't need to compute these cells. I can just say, fine, of your cells, of your edges, which is the closest edge you have to the goal? That's this one. I say, okay, cool. So I'm just going to add all these cells. I don't even bother to look at these because I know this entire block is valid. I can go through it and I know how close it is. So then I add all of its neighbors as contiguous blocks into the system. And so that gets a little complicated with the quad tree because how do you figure out its neighbors? Along this goal, this is technically a neighbor of this guy. So that can be a little weird. But if you get to that point, I could literally say, okay, let me look at this block. Now let me look at these neighbors. This neighbor, this is a block. And then this is a block on that block that has a neighbor of the goal. And based on that, I could just say, oh, these are the contiguous blocks I need to get through. Then you can run a smaller A star pathfinding for each block to see what's the most efficient path to get through that block. So that could be kind of interesting. And so I want to kind of take a look at that and see how that would work. And, you know, because y'all are here, you're going to take a look at it with me. Or, you know, if you don't want to, that's also totally fine. But that's what I'm going to go through. So the first thing I need in here is if I have a tree, it might be nice to know specifically which block a XY coordinate goes on. The reason for that is this entire quad here and then this entire quad, they don't talk to this quad. I'd have to go up the parent and down the parent to do that. Now I do have a method in my tree, set and get. These basically go through and loop through the current until we find something. So what that could be is if we find something that's got, and they generate children as they go into it, right? So what we could do instead then is the get actually shouldn't be generating children. Now that I think about it, that's kind of wasteful, isn't it? But, oh no, it's actually not creating them, is it? Because we're creating those in the set to create necessary children. If the child index is 0, then yeah, then we return the value. So instead of that, we could actually have a get that just returns current, honestly. And so I could just say get node at coordinate. And literally the only difference here then is this just becomes return current instead of the actual value. Why is that useful? Because once I get access to that, then I know its dimensions. And so I kind of know what I'm working with. So let's check out what that would look like. I'm actually going to, I want to take this entire thing and I want to copy this and I want to put this in a method called A star step. Okay. And then I want to go, because I don't want to lose it. And I want to go in here. And I just kind of, well, a lot of this code actually is still valid because I'm looking through the nodes. It's just how do we get our children that, or our not our children, but like our neighbors. Yeah, so this actually shouldn't be children. It should be neighbors. But let's just take a look at that. So to start off, I want to get rid of all of this for now. And I want to say, okay, you know, we're set, we're here. We're going to set that as complete. Let's just turn that off for now as well. So node equals 10 while complete. We're not at that point yet. So we're getting our node, and then I want to say tree node equals map.tree.get. What did I call that? Get node at coordinate. Get node at coordinate, and this is going to be our goal node. And what I actually should start off with here is that this queue needs to have now a width and a height. So I'm going to take this nodes to look at, and I'm going to take this and I'm going to pop it in here. And then, yeah, because I don't want to muck with this too much. This is already working. Don't muck with an algorithm that already works if you can't help it. Oh, nodes set in queue. See, this is the problem. If nodes to look at now. How do I enqueue this? Maybe I'll just leave it. You know, actually, maybe I'll just leave it because the A star doesn't care about the width and height, so it's just going to ignore it anyway. So that should be fine. Width 1, height 1. Okay, cool. So what I want here is first I want to find my node. Get node at coordinates. This is going to be node dot X, node.y, console.log, tree node. Okay, so we've got our tree node here. I go here, I take a step, it gets me my tree node. It has no children, and it has a height of 1, width of 1, etc. Because this is a single node, right? This actually has some value. Then I want to get all 4 of these, but I want to get them via the get node at coordinates. So I still pull in my children here, and I say, okay, filter the ones that are off the map. I'm going to take this off for now because I think I need to do this later. And then let's get our, we can do a const of this. Tree nodes equals children.map child. And then I'm basically going to say, this is not actually completely correct either. I'm going to need to change this at some point because we're going to have these that have different widths and heights. But that should be okay for now. Return map.tree .get node at coordinate child.x child.y .log tree nodes. And now, oh god, unexpected token at 219. What did I do? 219. Oh yeah, because this is all commented out as well. You know what? Let's actually do this. Let's not push these into nodes to look, but what I want to do is I want to actually take this node of tree nodes and change its value. Because you can do that directly. What we do normally is we set that quad tree and we say, okay, set this node, set this node, set this node, set this node. But you also just change the value and that'll change its color. Child dot value equals look at. And let's just see what that does. So I take a step. Now you can see this whole section lights up. That's kind of cool because if I look at this element, for example, I know that it immediately is the whole thing. I don't need to look through it. I can just look at this one block. Now the problem we get is how do we compute the distance? Well, the distance probably needs to be from every single edge to the goal, right? So I need to go all of these edges to that goal, and whatever is the shortest distance, that is going to be the distance to the goal. So let's take a look at that then. If we want to get our distance, distance equals null. And then I want to say let I equals child.x, I less than child dot width, I plus plus. Because now I'm going through the whole thing, right? Then I'm going to say, okay, we got to do this twice or check it twice. If we're going across the X, we need to do, yeah, we need to do the Y on the top and the bottom. So we're going to see here, okay, distance, shortest distance, distance, this should be inside the loop. Distance equals distance between points. This is now going to be I child.y to our goal node 8. And then it's also going to be child.y plus child.height. Because we need to look at both top and bottom. And we're going to do a similar loop for the verticals. And then what I kind of want to do is I'm going to make a little helper function here. Check distance. And then I'm going to say if shortest distance equals null, well then new distance is going to be the shortest distance because we didn't have anything. Otherwise, shortest distance equals math.min, new distance, shortest distance. Basically, if we don't have anything set, then whatever, oops, this is backwards, whatever they gave us is our new shortest distance. Otherwise, verify it's actually shorter. So then I'm just going to say check distance on all of these. And same thing here. Check distance. And then we're going to do the same thing for the y. It's going to be I equals child.y, child.height. This becomes child.x. This becomes now I. And this becomes child.x plus width. And then I. All right. And then let's console log the distance. Or a shortest distance, rather. Shortest distance. So I'm kind of curious what that gives us. Okay. So we've got, oh, it's all null. Well, that's exciting. Something went wrong there. Just make sure we're actually doing this loop at all, because something's wrong here. We are doing the loop. Okay. Just because it's null. Distance between points. Check distance, new distance. Oh. Because of this, I put that n in there. So JavaScript just magically created a new variable. Thanks, JavaScript. Okay, take step. 7, 9. I'd still get nulls here. I think this actually needs to be above or equal to. In most cases, I wouldn't want to do that, but some of these actually have, you know what? Some of these actually have a width of 0. I'm realizing that if they don't work properly. So actually what I'm going to do is I'm going to do a math.min or max 1. Because I want it to run at least once. Oops. This is going to cause probably some pretty big issues when I actually get into those things, but I kind of want to see. No, that doesn't help with these. What is this node? This is a width and height of 1. Oh, so I still need that up there. Child.x. Oh, this actually needs to be child.x plus. That's why. And actually, I probably, yeah, that would make sense then. Okay. Okay, cool. So now we have a 6, a 6, a 7, and an 8. And that 6, where does that 6 come from? This one is at 3, 8, and it has a height and a width of 1. So that's, I think that's this one, which kind of makes sense. The 6.08 is the one, so that's this one, 6.08, which also makes sense because it's slightly further off. So if we now throw these into the queue, shortest distance, what happens? Let's take a look. All right, take a step. Take another step. Oh yeah, so that actually, this needs to be changed. This tree node needs to be changed to complete. Node dot value equals complete. And just so we can see that we did that, take step, take step. Okay, so it handles that. Okay, it's probably gonna handle this one. Oh, that's not fun. Yeah, because that algorithm's kind of off now. We can't know if, yeah, this is probably gonna cause me, that's exactly. This is probably gonna cause me trouble later, but that's okay because that's my future problem. The reason I do that is because like at least 2 times out of 10, it doesn't cause me a problem. So then it would have been wasted effort. And then the other case, you know, basically I go through life putting out fires that previous me did and starting fires for future me. It's interesting, it's fun, and it gives me something to do. But yeah, no, it's I could definitely be more efficient about this. So now I'm realizing this is actually not helping us that much because of these are all singletons. But we can try it. So now these need to actually be checked appropriately to see if we've already got them in the queue. How do we do that? Well, we should actually know because these are actually tree nodes at this point. They're not coordinate pairs. So we should actually know if they're just in the queue. And so what I'm going to do, you know what I'm realizing? I can actually pull this map up and put it right here. Because then that lets me filter on the tree node. Here. Okay, so this is a wall. So then I'm going to say if element value equals wall, then return false. Okay, so that'll handle that first bit there. And I'm actually just going to comment the rest of these out for now. Because I just want to see if I deal with that wall piece appropriately. Take step. Oop, something broke. It did not like that. Oh, because I need that return true at the end, or else it totally filters it out. Okay, take step, step, step. Okay, so the wall's not showing up anymore. That's good. Now let's look at whether or not we've already processed the element. So I can actually just say if processed equals element. Because they're basically the same, it's the same tree node, right? Then they're found. And then this one, same thing. If nodes to look at contains node, I'm just going to say if node equals element. And I think that will just work. Because now they're objects, so I can do that comparison. Or it might explode dramatically. Let's see. Okay, that seems to have worked nicely, actually. Okay, we got this big one there. Take step. Ooh, look at that. That opened up. But it only opened up one of these. I wanted to actually open up all of these as well. And that's because the it only looked at these children here. When I'm looking at children, I actually need to do something more like these loops here. So let's actually do that. Let's say children equals, and then let's actually do a let on that just so I can override it. I'm going to say children.push. Grab this. This is going to be, I'm pretty sure this actually needs to be node. Node.width. This is going to be I. This is going to be node.y, and the parent is going to be the node. Similarly here, this is going to be the node.y plus node.height. Actually, this also needs to be -1. And this needs to be +1. Ooh, this is actually wrong now. I'm not so sure about this anymore. Okay, so we're going along this. The top one needs to be the y -1. That's it. The y needs to be -1. And this one needs to be +1. Okay, that works. And then we can just slurp this over here. And it's going to be the node.x -1. And this is going to be the I. This is also child. Let's make sure that there's node. Great. This is going to be node.x plus node.height +1, and then this is going to be I. And so now we've got a shit ton of children. They're not actually children, they're neighbors. I'm going to just rename that because that is bothering me. Okay, and then I'm just going to say neighbors equals neighbors.filter. And then let's see where the next place I'm using this is down here. Oh, I'm already mapped. I already did that map, so I can get rid of that. And then this actually can just still be neighbors because we're actually now just computing that. Okay, cool. I think that does something. Let's see what it does. Let's see if it's not completely broken. Oh my god. That looks wrong. That already looks wrong. Okay, so then the height, these do not +1 then. Okay, well now we know. Which also means that these are probably off. This is probably getting the wrong distance somehow. It's okay. We'll be okay. Take step. Okay, take step. Step, 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 step. Ooh, beautiful. Look at that. Step, step, step. And now it gets there. Different path. Right? Very different. And I mean, in this case, it was actually the same because this is either path is the same distance. But you can kind of see how now we processed a lot fewer entities because we didn't need to process that block. We just figured out, oh, we know we can get through this block. And we know it's not going to be expensive to get through this block necessarily. So there we go. So this is a slightly cheaper path. You notice it didn't handle the neighbor or the whether or not we're here. So what I actually want to do is what we need to do is we need to say, okay, const goal node equals map.tree.get node at coordinate 10, 8, and we need to see if our node is equal to our goal node. That's how we know we're done. And then in this case, instead of that map tree set, we're actually going to say current.value equals, oops, hat. Because again, and yeah, I guess we'll leave that in there. All right, let's do that. Let's see what that does. Oops. So that's not working then. Why isn't that working? Because the next one closest to this should be the actual goal. Let's try that again. Okay, we get here, here, here. Okay, so now I take a step. It processes this tree node. Okay, this is at 5, 2. All right, at 8, 8. Okay, so where's 8, 8? 0, 1, 2, 3, 4, 5, 6, 7, 8. Oh, that's this one that's being processed. Okay, next step. Why didn't we process this one? That's the thing I don't understand. Why didn't we process this one? Because this should have been 0, right? It should have had 0 distance from the goal, which means it should have been the next one to be processed. Let's see. I want to get rid of this priority queue print here. Oh my god, I keep opening this thing. So where is my priority? There it is. I don't want to look. Well, maybe I do want to look at that actually, because that's useful. The processing, where is this? This is 234. That's not helpful anymore. Maybe it is. Let's actually look at our child and the shortest distance. Okay, so we go here. Bam, 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 bam. Okay, so now this is going to be the source of truth. When I click this, it's going to process this. And so what happens here? Okay. This is 0, 0. Oh, wow. So they're all zeros. That's why. We've got a couple of them that have that 0. This is just the first one. This one has that 0 as well because they're right on the border. That's why. Okay. Well, that's more problematic then, but I guess eventually we should run through all those then, right? So we process this one. We process this one, okay. Then we process this one. We process, oh, we can't process it again. So this one should be, this is 10, 8. So this is the actual one. And now I get to, okay, cool. So that works then. That actually works because it just processes a couple of the others that are touching it because they also have a distance of 0 to it because they're right on its border. I could probably tweak the algorithm calculating the distance a little bit for that, but I'm not too worried about it. Actually, it'll just at most handle 3 additional neighbors before it gets to the goal, which is okay. This didn't work though. What is our current? Current. Oops. Oh, you know what? Because of current dot, it's probably because the current is null. Yeah, because it's undefined. All right. So if current, oh, you know why? Because it doesn't have the parent. Because this neighbor is never on there. So what we actually want to return here is, oh, but if we do this, we lose that object. That's a problem. I like that parent here. I like that parent thing. The other thing is I don't entirely like putting the distance on the child. Well, I guess we're not doing it anymore, but at some point we were putting the distance on the child. It'd be nice to be able to set some data on the tree that can get overridden, because the thing is, this is the map. If I put data on this, it's going to be there forever. So if I put pathfinding data on that, it's kind of messy because it's just stuck there. So what I kind of want to do instead, well, no, maybe that's all right. So let's just say dot for each element. Oh, this actually needs to be a map. So returns. Oh no. Oh yeah, it does need to be a map, yeah. Element dot data equals parent node. So now I'm just gonna put a data thing on it. And that return element. The reason I'm using a map also is for each doesn't return the array. So I actually do want to return it because I'm at the very top of this chain. I'm actually setting it equal to something. But yeah, this data then, I can ignore this. I can overwrite this. It has nothing to do with the map. Should be safe to do that. And let's see, data.parent. All right, let's try that now. No, not that. Okay. Undefined, cannot read properties of undefined reading parent. What is my current then? Let's just take a look at that, because that might be the issue. I kind of want to get the run set up for this because, like, okay. Ooh, here we go. Tree node, tree node. Oh, that's why, because this is the very original one. This is the one that I pushed. Here. That's the node. So actually what I want to do here is instead of that, here's my node. I actually want to be giving it the tree node as my parent, because that is actually the tree step that knows how to handle its stuff. Okay. The other thing I should also do is let's do this. And then that's just kind of that that optional chaining is gonna, because the first node is not gonna have data. So that should be fine, because then we know if we don't have that data, then we're at the end. Oh, something just, I just got an infinite loop. Oh boy, don't like that. Why would you infinite loop? Okay, why current? Well, current does not equal null. Current equals current data parent. Oh, which becomes undefined. That's why. So when we get here, that becomes undefined. So a secret to that is if you just do like this, null and undefined are equality equivalent. So this should be okay now. Now I got to open this up again. You know what? I'll just go into my history. I can't do history. Wonderful. Chrome, you're not being helpful here. You're really not. All right. Oh, there we go. Cool. So let's open up our here. Oh, no, it's still infinite loops. All right, maybe that's not true then. I'll just be lazy about it. Current does not equal to undefined. You know what? Actually, no. I could just use a nullish coalescer. That should be fine. Nullish. Copy. Let's kill that tab. Go here. Infinite loops suck. If this doesn't fix, I'm actually gonna start like actually putting out some print debug and see what the hell's going on. Nope, that's not it. All right. You need to like die. Thank you. Okay. So now I'm going to do, if you get an infinite loop, this is a thing you can do. Count equals 0. Count plus plus if count greater than 100, break. So that just, you have a sentinel. Your loop will never go over 100. I wouldn't leave this in the code, but I do want to just see what the hell is going on, because something is not going right here. And this should prevent an infinite loop, because at the most it'll loop over the same thing like 100 times. Oh. Now it just works. Okay, well, watch. When I delete this stuff, it's going to break again. I bet you will. Oh, you know what? That's why. It didn't work. It just kept on this one. Okay. Yep, that makes sense. Okay, 5. These are different coordinates. Great. Oh, do these point at each other? I think these might point at each other. Yeah, they do. So these are pointing at each other, and that's why we got that. That happened Probably because this is not working appropriately. That'd be my guess. But somehow these two ended up pointing at each other, and that should not have happened. Where am I? Oh, this is the wrong one. So, hmm. So when we put the element parent here of tree node, at some point it had one of its own. Okay, which one are these? Which one is this? Where am I even? So this is 3, 8, and 2, 8. Okay, so let's see. 0, 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 2. So these two, for some reason, when I go here, take a step, that first step adds this back into the queue somehow. And I'm not completely sure why. Let's see. If I take another step, just what's in our queue? 4, 7, 6, 7. Trying to find my original 2, 8. Here it is. Okay. So your parent is set to 3, 8 already. Already that's set. So that's kind of weird. I mean, I could fix that really easily by just saying don't do this if the parent is yourself, or like the child is like your parent. But I kind of want to find out why that's happening, because that means that this is not working appropriately. So let's see, console.log processed element. So, okay, I take a step. Okay. And this is saying, oh, that's why this is still the tree node. This is actually checking against what we get put into the process node. Yep, that's why. Because the process node doesn't actually get tree node. It was getting the other node. And so when we were doing that equality check, they weren't the same because it's actually just doing a memory index check. Okay, I think that probably fixes that issue. There we go. Oh, we got another, looks like another infinite loop here. Yeah. This is the same thing. It's going, oh no, this is 205. Maybe I should take that out, because that might have just been, let's just put a log here just so we can verify we're not actually getting an infinite loop anymore. Infinite loops suck. Okay. Okay, I did not get that. So that's fine. I'm going to comment out print. I'm going to comment out this print here. Take out that. Take out our count. And let's just see. Render drew. Yeah, it's fine. The render can draw. I don't care about that so much. All right. So then, now if we were actually doing like a decent path, we'd actually find, okay, what is the quickest way through these particular things? Not a super big deal to figure that out. But yeah, that's how you could do a path like this using that. So let's do this. And what I want to do, I kind of skirt the edges of this here. So now what happens? Okay, we find that. We go there. We go up there. Here. Okay, we see that. Ah, that's actually kind of interesting now. Because now it didn't take the exactly most optimal path, did it? It kind of went up here and then around. So the more optimal path would have been to go over here. So that's kind of an issue here, because this edge was closer to here, but what we're not doing is we're not taking into account the travel time that would have to go across here. So that might be something we want to add in there as well, and just say, oh, yeah, we've got this edge here, it's closer, but consider that you'd have to go across 4 other squares, and there might be a closer option. That would probably be a good way to do it. I'm not too worried about that right now, because you know what, it works. And this is a much more efficient algorithm, because it only went through, like you can see, it only went through a couple of nodes. It only had to go through a couple of nodes. What is this? 1, 2, 3. Yeah. So if you look at these, if we count these up, I would imagine it's less than what we'd have to do otherwise. So yeah, that's kind of what I have for today, honestly. Pathfinding algorithms. We went through two of them. We went through the A star, which is, not amazingly complicated, though you can see we did a lot of stuff in here. It's not complicated at its surface, but we put a lot of stuff in here, and that's kind of why I wanted to go over this, is to show you that just because something is simple on the surface doesn't mean that it's simple to do, and there's a lot of little edge cases that we had to build. Then we looked at this more efficient one, using our quad tree to kind of figure out what we could see and what spaces we knew were available to go through. Something that might be kind of interesting as well is if we actually generate a quad tree, because we've got our quad tree here, right? But that includes the goal node and this node. If we had other nodes in here that were like, maybe we had a flower, something, or like a field of wheat that you could walk through, we might want to generate a quad tree without those and just a quad tree with the obstacles, because then that would be more efficient to path through, because we're not worried about, like, if I had a flower here, all of a sudden this block becomes broken up into other blocks and it becomes less efficient to path through it. So that could be a thing that you want to do, is have multiple quad trees, one that holds your collision layer and one that holds your non-collision layer or your draw layer, so that you can actually path through that collision layer more effectively. But yeah, I mean, at this point, we got about 30 minutes. I wonder if, does anyone have any questions? Things that they maybe want to talk about? Fun little things they could think of to improve upon this? Should actually check to see if there's even anyone watching at this point. Well, we got 4 people watching. Okay, well, I'll wait a couple minutes. Oh, what happens with complex paths? Oh, that's a good question. So, like, with this particular algorithm or with A star? So I guess we could try A star. Let's see if we build ourselves a really complicated maze here. I am not good at maze building, by the way. So let's just make this one. Let's have like some paths that go off into other directions. With 2 valid solutions. Okay, let me see if I can do that. Yeah, let's make this. Let's add a couple of this is not a great maze anymore, but yeah, so let's do something like this. Oh, that's not, now there is no solution. Well, if I run that, that's not going to work. Okay, well, clearly I need the ability to delete walls, because I am not building this well. Let's go all the way up here to where we're creating the walls, which is, oh god, where is that? It's up here. Okay, so let's see. Equals map.tree.get chords.x chords.y. So then what I want to do is I want to say, okay, if value equals wall, then we're going to set it, set chords.x chords.y. We're going to set it to empty. Otherwise, we're going to set it back. We're going to set it to wall. So just now it's a toggle. Okay, so now, beautiful. All right, let's build ourselves a little bit of a maze with 2 paths. All right, so let's do our one path. Let's just build a room around this. Maybe let's have it go in here, kind of like that. All right, that is not an equal room. There we go. And then let's see. So our bottom path, let's have it be something like this, maybe. Sorry, I'm not amazing at drawing mazes, I'll be honest. Amazing at mazes. And then let's see here. And then like maybe let's have a sticky out bit here, and then something like that. All right, and then maybe we'll do something like this as well. All right, and then the top half, let's just do a massive fucking zigzag. I don't know how equivalent these actually are going to be. But what I'm hoping is that they'll be somewhat equivalent. Like that. All right, and then let's see what A star does. A star found that was kind of the shorter path. Okay. Now, let's see. I really need a reset button now. Let's see what the other algorithm does, which I'm going to have to step through. And sorry, yeah, the colors won't reset very well. Oh, yeah, you can see it really just goes straight for that other path and doesn't even bother with these. Because that other path is just, a lot of it's just more efficient. Yeah. So I think that's kind of why that path wins, is it's, what if I open this up? Okay, it doesn't really change anything. Because this, it's this wall here, I think. So if I remove that, then it goes through here. But it's just this, the fact that this wall is here, that it goes through that. The fact that this is not resetting every time is really bothering me too. Oh boy. Anyway. Yeah. So yeah, so the fact that it never goes up here, um, is why it always goes down to this bottom. So like if I go over here and make it come around the top, it comes over now here because that's a quicker solution than going around here. So you can see like it's not always, the thing about A star is like, at least the way that I've built it here, is it's not always going to give you legitimately the most optimized path. It's probably going to get you close though. So yeah. Another cool thing that we could do, I don't know if I want to do it now, but something else we could do, whoa, okay, I destroyed the goal, is you could put weights on these. So you could say like maybe this is a swamp, for instance, or this is a trap that you have to get through. So this takes longer, and you add a weight onto that, and all that does is you just add that onto the distance, and then it's more expensive to get through this tile. So the system will try to find other routes before going there. And that's pretty much all it is. These basically just have a weight of like infinity. Like you'll never try to go through them. Fun thing that I learned when I was first building A star way back in the day. I actually did set these to a weight of like 1,000,000, and then added that on, so the walls were 1,000,000 weight. If you box in the goal completely, then it would just go straight through the wall. Because it'd be like, well, there's no other way to go through, so my 1,000,000 path is clearly the shortest path, and it would just go right through. So not exactly what I wanted it to do. So that's why I have the walls is just like, nope, never. You can never pass this. This is impassable, because otherwise you will never get a situation where you could box it in. Yeah, fun stuff. Fun stuff. This is actually kind of an inefficient map at this point because of all these drawings. Something that might be better to have on here is multiple trees, because our original quad tree, right? So if I go here and I just run, my original quad tree here, there was no reason to break this up because it wasn't actually rendering any of that stuff. This path quad tree on top could have been, something that like is just another tree on top of that only has these little things and is more efficient in its way as well. But yeah, this is a fun little thing to do. I also want to show you guys while we're at it, we've built our map, and this is not in anything, right? So like we've built our map, we've got that all set up. I'll show you something that I have actually built. And let's get, this is actually in React, so I need to get an actual dev server up. Oh, it's taking forever. There we go. Come on, terminal. It's really chugging. This thing's saying, oh no, the CPU is not liking what you are doing. Because VS Code is just really a bit of a memory hog. I need a new dev laptop, honestly. Map. Run. Just let this build. And I'll show you kind of what this is about. So basically, this is the exact same canvas thing. This is that map, but this is React. right? So you have your layers, layer images, stuff like that. I am working on rebuilding this right now, so it's a little bit better, but I kind of want to show you what this does right now, if it, it ever builds, because this is actually what I use for stuff. It's a little inefficient because React doesn't play well with things that aren't actually HTML elements, and these are not actually HTML elements. But the render system of React is kind of nice in some cases for this because it makes it very easy to. You can see we have a click event, right? It's the canvas click, and it handles a bunch of stuff that way. But yeah, so if you've ever seen me do stuff in this, this is why I do that. It is a little hard to work with because you have these specific things and you can't just randomly draw whatever you want. Are you going to load? Is not going to load. It don't want to load. Webpack. Why are you taking so long, Webpack? I think it's just going to take too long. But anyway, that is what I actually use for this stuff rather than these particular things. But this is more efficient. Yeah, Webpack is the idea. I should move it over to Vite, and it'd probably be a lot faster. But yeah, so this map is a little bit more efficient because it's that raw JavaScript and doesn't have the React render loop. The issue though is that it also doesn't have that nice. Where am I going? What am I looking for? You have to keep rendering it, right? Every time you do something, you have to remember to re-render it, which honestly isn't that terrible. But yeah. Yeah, okay. What is taking up all of my CPU? I kind of want to figure that out. There we go. Wow, that really, it was like the task manager is going to take forever. Bing, 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 bing. What is taking up the CPU? Oh, it's OBS. Of course it's OBS. OBS is such a CPU hog. That's okay. I'd rather the video be clear and all that stuff rather than anything else actually work. Okay, well that was, just a bunch of me faffing around. Anything else anyone wants to look at with this that we can do in about 20 minutes? Yeah, pathfinding's fun. I don't know. I looked up a couple other pathfinding algorithms, and they like gaming pathfinding algorithms. There's another one that they do where the whole thing, rather than a grid, it becomes like a bunch of shapes. So they have actually, it's kind of similar to the quad tree idea, but it's more like a bunch of triangles that indicate the navigation mesh. The thing about the navigation mesh though, in that case, is you have to have like you almost in a lot of games that use it, you predefine that navigation mesh. So it's not defined on the fly. It's when you build the map, the system generates those navigation meshes and figures out kind of the most optimal way to move between points. And that actually works kind of nicely because you can tweak that. And let's say you have a map, like maybe some Fortnite map. Actually, it probably wouldn't work with Fortnite because that has destructible and buildable terrain. But let's say like a Team Fortress 2 map, and you need to know like what's the quickest way between point A and point B, and it's not working the way you expect. You can just go in and tweak that value. I went over Dijkstra's algorithm a little earlier at the beginning, so that was kind of what this is about. A star is actually a rendition of Dijkstra's algorithm, because it is basically on a rectangular graph where everything is connected at the orthogonals. So yeah, we went over Dijkstra's a little bit. I have used it for navigating graphs. It's interesting. It definitely leads into stuff. I like A star better because it has more applications for me personally, but I think the biggest time I've worked with something that was using Dijkstra's algorithm was when I was building networks, or not building networks, but I maintained networks, and we used it for determining the most optimal path to get over the hill. So yeah, I'm familiar with it, and we did cover it in the beginning, so definitely feel free to rewatch that once I put the VOD up. Yeah, all right, folks, I think I'm going to end it here. Next on, what is that going to be, the 21st? Let me just check the calendar. Yeah, the 21st, we are going to have a recruiter that is going to be on stream, and those of you in the Discord have already put up a bunch of questions for them, so they're going to go through and similar to that other interview we did, they're going to be doing a little bit of a presentation, answering your questions, and yeah, hopefully that'll give you some insight into how that process works. So thanks for watching, folks. I know we're closing a little early, but you know, I've done what I need to do, so I'm good. So yeah, thanks for being here, folks. See y'all next time.